Hello, gentlemen. Happy Monday to you. Last class you worked on Charles' law calculations. You did a worksheet. We will be going over that worksheet next class period. Today, I want to introduce you to the ideal gas law. So we're going to use Boyle's law. We're going to use Charles' law. We're going to use that combined gas law. And that gives us what's called the ideal gas law. Next class, we'll talk about what an ideal gas is exactly. And we'll also talk about the constant that is part of this equation and where that constant comes from and why it makes sense in the equation. All right. So let me introduce you to the ideal gas law. All right. First, we need to remember what standard temperature and pressure is. All right. So standard temperature and pressure. Remember, standard temperature is 0 degrees Celsius or it's 273 degrees Kelvin. Anytime you want to convert Celsius to Kelvin, you just simply add 273 to degrees Celsius, and that'll give you the degrees in Kelvin. All right. Now, standard pressure, remember, is 1 atmosphere or 14.7 pounds of pressure per square inch, or 760 millimeters of mercury, or 101.325 kilopascals. Right. So this is the ideal gas law, and again, today I'm just going to give you the equation so you can start working through some of the calculations with the equation. And then next class period, we're going to get more into it. We're going to talk about the equations. I'll give you the answers, and we'll go over this together. But I will check this, so make sure that you work together or you work on your own, and you finish this worksheet. That'll come out right after the video, okay? So, PV, that looks familiar, right? PV, right? That's Boyle's law. Remember that P is pressure. And in this equation, the ideal gas law, it's always going to needs to be in atmospheres of pressure. All right, and volume needs to be in liters of volume. PV equals N. N represents the mass of the gas in moles. The R is a constant. It never changes. Again, next class period we'll talk about why this makes sense. And then temperature, and the temperature will always be in Kelvin, so make sure you're adding 273 to degrees Celsius to get your degrees in Kelvin. Now the constant here, it's not going to change. It'll always remain the same. And the constant is 0.0821, 0.0821 atmosphere liters. That's atmosphere liters over mole Kelvin. And that will remain constant at all times. Now, when you get a word problem, and you understand that that word problem is giving you pressure, volume, and mass, and asking for the temperature, or it's giving you the temperature, the volume, and the pressure, and it's asking you for a mass, you know that you are going to use the ideal gas equation, which we refer to as PIV-NERT. Yeah, PV equals nRT, PIV-NERT. All right, but you must always convert to atmosphere, liter, moles, and Kelvin. So you're always going to convert right away before you can plug anything into this equation to make it work. So let's do an example. All right, there you can see it. All right, so it's kind of a bad angle. All right, so what mass of argon gas can occupy a volume of 3,500 milliliters at a pressure of 845 millimeters of mercury at a temperature of 35 degrees Celsius? So the first thing is we're going to write down our givens, right? So it gives us pressure. So we know pressure is 845 millimeters of mercury. It gives us volume, 3,500 milliliters. N represents mass, remember. And what is it asking for? What mass? Okay, so we don't have mass. Remember, mass is always in moles, so we're trying to find out how many moles of argon gas. The R is the constant. This won't change. 0.0821 atmosphere liters over mole Kelvin. And then finally, temperature, it gives us the temperature, 35 degrees Celsius. What must we always do? We must always convert to atmosphere, liter, moles, and Kelvin. So let's do that, all right? Take a look at our equation once again. So we'll start down here with the easy one, right? Temperature, all we need to do is add 273, which gives us 308 Kelvin, right? Okay, we know the constant's never going to change. We're looking for moles. Here's a volume. Okay, volume 3,500 milliliters. What do I need my volume to be in order to input it into the gas law? Yeah, it needs to be liters, right? So let's convert it to liters. So we know that in every 1 liter, there are 1,000 milliliters, right? So now we can cancel out the milliliters, okay? We can divide, and of course, this will give us 3.500, significant figures, right? Liters. 1 liter over 1,000 milliliters is how we got to this, okay? All right, now up top there, I'll try to squeeze it in, 845 millimeters of mercury. Remember, we need it to be in atmospheres of pressure, right? So we know that in 1 atmosphere of pressure, there are how many millimeters of mercury? Well, here it says it right there, 760 millimeters of mercury. So we can put 760 millimeters of mercury, right? We can cancel out the millimeters of mercury, and if we do use our calculator, we plug that in, we're going to get to about 1.1 atmospheres of pressure. All right, so here we have it. We have atmospheres, we have liters, we have our constant, we have degrees Kelvin. We're good to go. We can put it into our ideal gas law. So the pressure times volume equals nRT, right? So what do we need to do? What are we trying to find? We're trying to find mass, right? So if we're trying to find mass, which is N, we need to isolate N, right? And if we need to isolate N, then of course we need to divide both sides by RT. So let's write it out here. Ivner. All right, and we know we need to find mass. So if we're trying to find mass, we're going to divide both sides by RT. Divide both sides by RT. These will cancel out. So then we have PV over RT equals our mass. Which you can't see. There we go. All right, so we have PV over RT equals N. So now we can plug it in. Okay, we know our pressure here is 1.1 atmospheres of pressure. Our volume is 3.500 liters. All right, and then that's going to be over, it's going to all equal the mass, right? And then it's going to be over RT. We know that R is 0.0821. That's atmosphere liters over mole Kelvin. All right, and then T is 308 K. All right. Well, there we go. Now we've set it up into the equation. Okay, and now we need to calculate. Okay, so if we calculate this, you'll see that we can cancel some things out. Okay, we can cancel out atmosphere. We can cancel out liters. So here's atmosphere. We can cancel that out. We can cancel that out. We can cancel out liters and liters. Okay, now we have mole and Kelvin, but we can cancel those Kelvin out as well. Kelvin is here, and Kelvin is there, so we can cancel those out. Okay, so a little bit of algebra. Okay, we're going to have to work on setting the problem up properly and just make sure we're canceling out units. And obviously, yeah, we want to be left with moles. Now we multiply across, we divide by the bottom. All right, and what we're going to end up with here is N I guess let me just put it here. How much argon gas is left? It's 0.154 moles of argon gas, right? Because everything N is in moles. Now, it says what mass? Usually mass might not be in moles, but we can convert it to grams quite easily, right? So if we have 0.154 moles, we can just take a look on our periodic table, right, and convert it, because we know that in every 1 mole of argon gas, there are, I think it's 39, let me check real quick, 39, yeah, 39.95 grams. And if we calculate that out, we can see that there will be about 6.15 grams of argon. All right, I hope this helps, guys. Work on that worksheet. Plug it in, see if you can set up the equation as best you can, and we'll go over these next time we meet. All right.